Welcome back, everyone. So tell me, did you survive the operational diagnostics trenches from our last lesson? I really hope so, because today we're taking a massive leap. This explainer is brought to you by Forge College, and we are officially moving away from just, staring at red error logs in a total panic to actually architecting real solutions. Today, we're designing node deployment and RPC interaction strategies. Let's get right into it.
I absolutely love this quote, and it perfectly sets the stage for what we're doing today. Seriously, think of yourself as a city planner right now. Knowing that a specific intersection, or, well, in our case, a node's CPU, is maxed out, that's kind of useless unless you actually know how to redraw the map. So today, we're translating all those diagnostic bottlenecks we talked about into a concrete, highly scalable architectural blueprint. We are building the metropolis.
Here's our 6-step master plan for today. We'll go from diagnostics to deployment, map out node topologies, choose our RPC pathways, scale reads versus writes, do some real-world endpoint testing, and finally, define your final architecture. Okay, let's jump in. Section 1. From diagnostics to deployment, bridging the gap. To bridge that gap, we really need to get our vocabulary straight on two foundational concepts. First up is your deployment topology. You can think of these as your zoning laws, right? It's the physical arrangement, the geographic distribution, and the role assignment of your servers. Second is your RPC pathway. These are your roads. It's the exact route that a client request travels to reach those nodes and then get back. You see, you can have brilliant zoning laws, but if your roads make absolutely no sense, well, you're still going to end up with a massive traffic jam. All right, Section 2, mapping node topologies, the zoning laws of Web3. Okay, so we really must separate our deployment into two distinct axes. First is the role axis. Basically, is this node a validator, an RPC node, or an archive node? Second is the exposure axis. Is this node entirely private, internal-facing for your own team, or public-facing for your users? Splitting deployment into these two axes is just absolutely crucial. It helps us independently reason about security, maintenance, and performance without tangling them all up into one giant, messy knot. Like, for example, you can build a tightly coupled, totally private cluster of validators with literally zero public exposure, acting purely as your secure consensus engine. Meanwhile, you route all your noisy public traffic to horizontally scaled RPC nodes sitting on the outside. Moving right along, Section 3, choosing RPC pathways, directing the traffic. So we have three archetypal pathways here, and let's start with the first one, the direct single-node connection. I like to call this the dirt road. A client sends a request, it hits a single node directly, and, well, that's literally it. Now, the pro here is that it completely minimizes indirection. It can give you exceptionally low median latency just because there are no middlemen. But the con, oh man, it is highly dangerous. If that single node gets overloaded, you have absolutely zero failover. Your app just crashes and your users immediately take to Twitter to complain. So it's great for local testing, but it's terrifying for production. Because of that, we usually upgrade to pathway number 2, client-side multi-node. Here, if the primary node degrades, intelligent logic living inside the client SDK catches that error and automatically round-robins the request right over to a backup node. This adds a really fantastic layer of resilience. But be warned, this requires very careful retry policies. If node A goes down because of a massive global traffic spike, and your client immediately hammer sends that exact same traffic to node B without any kind of backoff strategy, you're just going to knock node B offline too. Congratulations, you've just successfully DDoSed your own infrastructure. Not great.
And that leads us to the ultimate heavy hitter pathway, the centralized gateway. Imagine a massive, highly intelligent toll booth. The client hits the gateway, and the gateway does all the heavy lifting. It checks node health, enforces rate limiting, handles caching, and then safely routes the request to the optimal backend node. This takes a massive burden off your client code, centralizing your observability and your security policies in one convenient place. The trade-off, though? Well, the gateway itself becomes a single operational surface. Basically, if the toll booth goes down, the whole highway shuts down.
Section 4, scaling reads versus writes, commuters versus VIPs. Okay, so the absolute most critical point here is that we must separate our traffic. Read traffic is kind of like your daily commuters. They're cache-friendly, they can totally tolerate eventual consistency. Meaning, if a read replica is a few milliseconds behind the main chain, it's usually totally fine. Because of this, read traffic scales beautifully horizontally. Write traffic, on the other hand, that's a VIP motorcade. When you're submitting a transaction, you need strong consistency. That transaction absolutely must reach the leader, and it requires careful retry semantics and nonce management to ensure it isn't dropped or accidentally duplicated. If you mix these two types of traffic on the exact same nodes, those commuters are going to get right in the way of the VIPs. You simply must separate them.
Section 5, Real-World Endpoint Testing, the Master Zoning Table.
So here is your master blueprint. Let's walk through some real-world use cases. If you're building a low-latency market data consumer, your primary topology should be edge RPC nodes. You want geographically distributed nodes to drastically reduce round-trip time, making your reads blazingly fast, even if you have to accept a slight risk of sync lag. But if you're building a massive enterprise auditing application, you really don't care about a few extra milliseconds. You care about reliability and unified metrics, so you'd use a centralized gateway. Finally, if you're running a high-frequency order book settlement service, you absolutely need a dedicated write pool. You want a highly tuned pathway that can handle immense back pressure and get transactions to the leader flawlessly, even with the added deployment complexity.
And finally, Section 6, your final architecture. Setting up the speed traps. We know the topologies and we know the pathways, but how do we definitively prove our architecture is actually working in the wild? Well, to justify our routing logic, we need hard data. What you're seeing here is the output of a simple but highly effective node.js health probe. By hitting a JSON RPC get health endpoint, we can continuously monitor 4 key metrics: the target URL, the HTTP status code, a Boolean OK success flag, and crucially, the latency in milliseconds. Honestly, you should be running a probe just like this inside a CI job or a cron task to build up a solid historical latency baseline. And that baseline really matters. Just look at these mock latency results. If your active health probe is showing that your edge node is returning requests in a blistering 25 milliseconds, while your gateway is taking 85, and your write pool is lugging behind at 120, your client SDK can use this exact real-time data to dynamically route all your read-heavy market data straight to the edge node. Basically, you're using live operational telemetry to drive automated architectural decisions in real time. It's awesome. As we wrap up this explainer, I really want you to burn these 3 golden rules into your mind. Number 1, split your read and write traffic to reduce contention, period. Number 2, centralize cross-cutting concerns like rate limiting and authentication right at the gateway level to keep your clients simple. And number 3, instrument aggressively. Track your latency percentiles, your 5x error rates, and your queue depths. Remember, telemetry is exactly what makes a static deployment dynamic. I want to leave you with a bit of a provocative thought to chew on today. If your diagnostics suddenly show a massive 200 millisecond replication lag spike on your primary edge node, what automated routing action does your architecture actually trigger next? Think about it. Does it round robin? Does it trip a circuit breaker? Ponder that as you finalize your deployment blueprints. And hey, if you want to dive deeper into failover automation and a ton of other Web3 concepts, be sure to visit forge.college. This explainer was brought to you by Forge College. Thank you so much for learning with me today, and I will see you in the next one.